Today is for our speaker. So we are joined live in Pasadena, California at NASA's Jet Propulsion Laboratory by Bobak Ferdowsi. So he is a spacecraft systems engineer. He's held tons of jobs at NASA, but right now he is a fault protection lead, which means that in systems with thousands of things that can go wrong, he makes sure that they don't. We're so happy to have him back. And so without further ado, thank you so much for joining us, Bobak, and take it away.
Hi guys, and thanks. You'll have to show, how do I project my presentation?
On the bottom of your screen, there's a little green square, share screen.
Yes, all right, there it is. We'll do that. Thank you. I just got to pick the right presentation and not one of my work presentations.
Get NASA secrets.
Okay. All right. What does this look like to everybody right now?
Right now, I just have a line that says, oh, there you go.
That's the wrong presentation. Cool.
Presentation. Okay, we won't tell you.
No, that's fine. That way you didn't see anything that important. Why is this one not coming up? Because it's on the wrong side. There we go. How about this one?
The one that starts with whoops?
Yeah, that's the one. Excellent. All right, guys, we did it. Okay, yeah, so I am a fault protection engineer, and I lead a small team here on a project called NISAR, which is a joint mission between NASA and the Indian Space Research Organization, or ISRO. It's an Earth orbiting satellite that will launch in about 2 years. The idea is to look at sort of environmental changes here on the Earth and understand sort of the impacts of both ourselves and, of course, natural events on shorelines, forestation, ice melt, all those sorts of things. It's our first real major partnership with India, and we're sort of combining to build the spacecraft and operate it together. So it's kind of got its own sort of unique set of fun. And then our team is largely responsible for sort of figuring out, describing how the system should work, which is right, like you sort of build a system, if you kind of imagine, like you know, you just think your computer or whatever, right? And then you want to create a sort of an experience that you're expecting to have with it. You know, for example, for our spacecraft, we want them to be able to communicate routinely. We need them to sometimes deploy certain hardware. So for our spacecraft, there is a giant, about 30 foot in diameter or 12 meter in diameter reflector that we have to open up in space. So it opens from about the size of a sort of like a poster tube, all the way out to this thing that's about 30 feet across, that will allow us to reflect the radar measurements. And then that's very challenging, and so we need to like sort of describe how the system works. And then of course, because it's super difficult and because space is sort of, you know, we don't always have communication with our spacecraft in real time, we have to figure out ways to have the spacecraft be autonomous and do things on its own, and that includes especially when things go wrong. Sometimes here on Earth we can't react fast enough, so we need the spacecraft to sort of take care of itself. It doesn't always have to fix everything, but at least it needs to get it to a place where it's safe and okay to operate, and can tell us on the ground what went wrong. So this kind of presentation is just a little bit like describing that and how we got here in spacecraft and some of the more significant kind of mistakes we've made along the way. And I hope that you guys will kind of learn like we do about how to learn from your mistakes and make things better. So we'll start out with some real simple things. This is a great video. Just enjoy this for a second. All right, so that cat's fine. But how many of you guys have had sort of an issue where you've made a mistake or hurt yourself or done something like, you know, attempted something like riding a bicycle, like for me as a kid, where you sort of had an issue? Yeah, a quick show of hands maybe in the classrooms. Yeah, nice. So I remember when I was 10 years old, I got in a pretty bad accident on a bicycle. I got hit by a car, and it would have been easy for me to kind of give up on bike riding altogether, obviously, be like, why would I ride a bike again? But instead, I was like, you know, what can I sort of learn from that mistake? And I, you know, made sure I wore helmets and tried to be a little bit more cautious on the road. I still bike to work today a lot of times, so it's great. But it's one of those cases where we had to, like, there's a chance to sort of give up on something and a chance to maybe learn from that mistake and figure out what you could do better to protect yourself in the future. I've also made a number of mistakes with money over the years. Sometimes, like, you shop for something and you're like, this seems like a really good idea at the time, and then you use it only once or twice, and you're like, oh man, this was a regrettable decision. I spent some good amount of money on this and I never ended up using it that much. So that's another kind of like mistake that you can make. We've definitely made those mistakes sometimes in spacecraft. And of course, I've also worked on missions where we have nearly lost spacecraft because of some of the choices that we made, sometimes with the best of intentions, and occasionally not working out the way we had intended it to. So this can be very expensive. I'm assuming none of you guys, I mean, maybe raise your hand if you've ever almost lost a spacecraft. Okay, no, all right. So JPL has had a number of pretty like kind of incredible experiences with near losses or losses of spacecraft. And it starts kind of the story that I'm telling you. We've lost spacecraft all the way from the beginning, obviously, when we were first learning how to do spacecraft. But even after 20, 30 years of experience, we still managed to lose and or have issues with our spacecraft. And Mars is no exception. So as we started to kind of do more and more Mars missions in the 1990s, we had a number of pretty significant issues. These are just some like highlights from the websites at the time of some of the issues that we had. And I'll like talk about these for just a little bit because I think they're really cool stories. But let's take a step back and like, why Mars? And so for a lot of people, I think Mars is one, it was very early kind of to be found in the night sky as something that clearly didn't move like a star. So we figured out that it's a nearby planet. And it was one of the first things that you could see with some detail if you had a telescope. So even if you have a binoculars or telescope today, you can actually see quite a bit of the features of Mars, especially when it's close by. But with sort of early telescopes, you could still detect or find, on the surface, all these like kind of features, darker parts, lighter parts, craters, things like that. And some of the early sketches, drew this sketch in particular by Schiaparelli, who was an Italian astronomer, drew these sort of crisscrossed lines that sort of resembled canals. And also in the translation, the Italian for canali got translated to canals instead of channels in English. And that sort of implies that it is like some sort of, alien, in this case, Martians, are maybe responsible for creating these features on Mars. So instead of being naturally occurring, they said, what if these are like roads or some sort of, tunnels or things like that the Martians are using to travel? And that kind of seeded a lot of the initial science fiction, right? So the War of the Worlds, where the Martians come to invade the Earth and things like that, gave like this idea of a world that may be full of life and maybe, just life that's kind of similarly intelligent to ours. So we sort of started there, and it makes sense, right? Because Mars isn't that much further from the sun. So it has kind of a similar, climate at some levels, the temperature-wise, as Earth. It's about the same size as Earth, not much smaller, like in the scale again of planets. So it's it's a rocky world. It's something that you could stand on. So it made sense that we would believe that life could be in a place like that. And so we started to send missions to Mars. And these are the first pictures that they turned back, took and sent back. This is from Mariner 9. And you can kind of see the features are unfortunately, you can see some of the craters, you can see some of the ridges, but what you don't see is any evidence of life or anything that even remotely looks like a world that's alive. This looks like our moon, sort of dry, very, lacking any water features, lacking any sort of thing that shows you that this world is alive and vibrant and things are happening on it. But scientists didn't give up, and so luckily they sent back missions a couple years later, and we found, again with another Mariner spacecraft, very clear indications that some sort of liquid must have flowed on the planet at one point in the past. So you can see here things that look sort of like rivers or delta features on Earth. So you can see like also that there's these large crater walls, and something has sort of broken down the crater walls. So this implies like a planet that at one point, maybe not today, but at one point in its past definitely had a lot of water and a lot of kind of exciting things going on. So that, then sort of makes the momentum go a little faster. And just a short few years later, we sent 2 landed missions to the surface of Mars, Viking 1 and Viking 2. And these are the first robotic missions to successfully land on the surface, and they're super ambitious. Like it's like mid 1970s, which means they're really built in the late 1960s, early 1970s. And they carry each 3 instruments that are designed sort of to help us look directly for life. So the 2 main instruments are kind of life detection instruments, and the 3rd instrument is looking for organic chemistry, which are like the building blocks of life as we know it here on Earth. And they were, unfortunately, they found sort of inconclusive evidence. One of the instruments definitely said no evidence of life. The organic chemistry detection actually also showed no evidence of organic chemistry. And there was one instrument that sort of had ambiguous results in looking for life, which some people argued was evidence of life. But the problem with science, of course, is that you need conclusive evidence. You can't just be like, well, this could be life, but it could also be a chemical process. And so we needed to have all those things. And so at some level, like, even though this mission was very like technically successful, we landed something on Mars, we were able to do science on Mars. It also didn't necessarily help that the answers were conclusive, and we had spent so much money and so much efforts into making this work. And so you kind of see Mars go away as a high priority for a couple of decades. We sort of got there, we did it, and then we're like, oh, well, maybe it wasn't worth all the effort. But in the 1990s, people started proposing more missions to Mars. And the idea was, what if we started kind of more at the fundamentals, right? So what if we go to Mars and we just look for like the really basic things, like, is there water? Was there water in the past? Because we know life here on Earth requires water. So we were like, well, maybe we'll just start there. Like, let's not go directly for life. Let's go for some of the basics. And in 1997, on July 4th, 1997, JPL, the facility specifically that I work at, landed this very small rover. This rover is about the size of a microwave. I know it's hard to tell the size of the rock where the rover is in this picture, but it's about the size of a microwave. And it demonstrated really for the first time that we could drive on Mars. So previously the missions had just landed on Mars, and now we demonstrated that we had the ability to sort of go around Mars, which is pretty significant, because if you land, of course, in one place, you're sort of limited to how much you can do. It's just exactly what's in, arm's reach. But if you could drive around, you could sort of go to different types of environments and maybe see different types of histories on Mars. And so this one kind of like, as I said, demonstrated that first ability. And we landed it with airbags at the time. So we got into the top of the atmosphere, we slowed down, we had some parachutes, and they were like, we didn't have a great way of landing it softly on the surface. There were a lot of reasons I can kind of describe to you in the next video why. So we said, we'll inflate some airbags, we'll drop it, and it'll bounce around, and eventually it will settle down and land, and then we'll drive off of the airbags into the surface. So this proved the technology kind of for us. And then we followed that up with a couple missions. But in the meantime, we had a number of failures in the 1990s. So this is one of the first failures. This is Mars Observer, and it is a spacecraft that was designed to get there. We're sort of in this paradigm of like, let's build more spacecraft to go to Mars. Let's build them quickly and cheaply, and we'll learn from the mistakes, and we'll just keep doing stuff and iterating. So of course, sort of like, I wouldn't call it quite prototyping, because obviously it's a Mars mission. We don't want to prototype, but the idea was this would be the first of many missions to Mars. Don't spend billions of dollars on one mission that does one thing. Instead, break it up into 10 missions, keep going back, keep improving instruments, keep taking advantage of all the changes that are happening in technology. And so this mission specifically took a satellite that was designed for Earth, and they tried to make it applicable to Mars. And they were like, what if we take this Earth orbiter and then we like modify it with a bigger solar panel, we add some Earth, some Martian observing instruments to it, and we ship it on its way. And sure enough, they were pretty successful. So when they launched this thing, right, it gets all the way from Earth to Mars. It's actually a day before they enter the orbit of Mars when they encounter their first big issue. And that issue is the way the system is designed. In order to get into orbit around Mars, you're actually going too fast. So when we send a spacecraft from Earth, you're going way too fast, and you will actually fly by Mars if you don't slow down. And so you need an engine to basically slow yourself down enough to get caught by Mars's gravity. And that engine existed in the Earth satellite. It was a reasonable sized engine. But what they normally do on Earth is you launch it, and within a couple of days, you basically charge the engine, right? You open up all the valves that are, allowing fuel to flow, and within a couple of days, it's sort of an operational engine. In our case, we said, well, we don't need to do this early. We'll do it when we get to Mars. And so they prepared the spacecraft to kind of get its engine ready. And when they did that, they had to fire these things called pyros. So like, pyrotechnics, like fireworks. We also have very small versions of those on spacecraft that allow us to sort of have things that are physically very hardly connected. You fire a pyro and it like cuts a bolt, right? And that allows something to open up. In our case, it was allowing the propulsion system to charge. And they said, well, the pyro, when you do it, there's like a little bit of an explosion, a very small explosion. It's controlled, but there's a shock to the system. And certain things like the radio, maybe, we don't want to have the radio on during that time because it could maybe damage the radio, or it would maybe make us lose signal. So they said, listen, here's what we'll do. We'll turn off the radio, we'll fire this thing, and then we'll turn the radio back on. And then we'll talk to Earth and everything will be, great. And what they did was they turned off the radio, they fired the thing, and then we just never heard from the spacecraft again. And that was the last anybody ever heard from this mission. And that is, we don't know exactly what caused it, but we started to go back and try to figure out from the design what could have happened, right? And we think there's a couple of things. Maybe some of the propulsion system got damaged and the spacecraft started to spin. And it's designed even to fix that, right? So we're smart people. We're like, sometimes spacecraft get accidental spins. Build in the ability to stop your own spin, and maybe the spacecraft did it. But one thing the spacecraft didn't do is, after stopping its own spin, try to recommunicate with Earth. It was never in the design. No one said, oh, if you do this, you also need to try to communicate with Earth again. So we don't actually know exactly what happened. And we theorize, again, like from the design, this is what broke on that system. So we actually, at some level, you couldn't learn that much physically from the spacecraft. But one thing you could learn was that if you have major events like this, you should always ensure that you have communication coverage, because you cannot learn from a mistake, for example, that you have no information about. And this became a real driving design for a lot of our missions, like Curiosity and other missions that I worked, is how do you make sure that when you're doing these intense things, when you're trying to reconfigure your spacecraft, or get into orbit around Mars, land on Mars, go anywhere in the solar system, how do you make sure that you can talk to the Earth and at least tell us what was going on when something went wrong, right? Because then at least we can learn from that mistake. So that was actually, in its own level, a mistake that we had to learn from, but the very hard way. Okay, so a couple years later, it's now Mars Climate Orbiter. You guys are a little young to remember this, but this was one of the more embarrassing mistakes for NASA at the time. It's still kind of embarrassing if you look it up. And this orbiter, kind of see a couple of things that are interesting about it. One is it has a solar array on one side of the spacecraft. And for those of you guys who don't know this, the sun actually has winds associated with it, solar pressure, right? So as the light expands from the sun, it blows essentially on things, and it creates a small amount of pressure. And so this solar array here actually acts a little bit like a solar sail. You get a little bit of force on the array, which actually turns the spacecraft, because it's pushing harder on the array than it is on the body of the spacecraft. And so it rotates the spacecraft. And so every so often, the spacecraft was designed to do it. It would rotate a little bit, and then it would correct its rotation by firing a thruster and pointing it back at Earth. So no problem. We have this issue. It slowly rotates. No worries. The onboard system is designed to turn the spacecraft back to talk to the Earth. Once again, hey, great job, everybody. We're really smart. But it turns out that this spacecraft had another very kind of hidden flaw, the one that's really embarrassing, which is the engines are typically designed to, when we kind of buy engines and the folks who work on propulsion systems, they tend to do this in imperial units. So like, pounds of force that the engine thrusts, right? And our systems are usually designed to use metric units. So we talk about how many newtons the engine is. And it turns out in the code, when someone wrote the code for how much control to do, they thought that the number that the propulsion guys gave them was a Newton measurement and not a pound measurement, or a pound foot measurement. And so they coded it up incorrectly. And here's the thing, it still actually worked for the most part. It wasn't that the spacecraft wouldn't turn correctly. It did, it's turning just fine. It's that over time, every one of those turns gave the spacecraft a little bit of momentum, right? So even though you're turning ever so slightly, you don't turn perfectly. You actually also get a little bit faster because you're firing your engine. And over the course of the 6-7 months of the mission, the getting from Earth to Mars, it started going faster and faster, and we didn't exactly know where it was. And it turns out, because of the small difference in the calculation from the newtons to pounds, it was not in the position that we thought it was when we were supposed to be at the top of the atmosphere at Mars and to slow down and get into orbit. And so we don't actually, once again, we don't know exactly what happened, but we know that the spacecraft wasn't in the right place at the right time to get into orbit around Mars. So it's possible on the one hand that it skipped off the top of the atmosphere, so that it just sort of, it hits the top of the atmosphere, it basically ends up spinning around because it's hitting the top of the atmosphere and flies off into space, or it hit the atmosphere and burned up in the atmosphere and is somewhere as wreckage on Mars. We don't know. And so once again, we learn a lesson from this one, this time a little bit different, which is one, of course, be very specific about the units that you're using, which is a good life lesson for all of us. But also we can use radio data to tell us exactly where the spacecraft is and how fast it's going. And so now all of our spacecraft take advantage of using these giant antennae here on Earth to basically do triangulation. So you can point multiple radio antennas at it, listen to exactly where it is, and then from using 3 or 4 antennas, exactly figure out, sort of like triangulate where its position is. And so we now do that on all of our missions. Okay, and another one that happened the same year was called Mars Polar Lander, and this was our attempt to land kind of in the North Pole of Mars, where we saw this kind of carbon dioxide ice, right? The polar caps of Mars, they're actually, they look very beautiful and kind of like icy-like, and there's actually water ice in them as well as carbon dioxide ice. But the idea was to land near this pole and be able to scoop up the surface and demonstrate what the composition of the polar caps was, and again look for direct evidence of water on Mars. And this mission works like 99.99% correctly. Like we get all the way to Mars successfully. We come in with a heat shield, top of the atmosphere. You're going 10,000 miles an hour. You're slowing down. You open up a parachute. Parachute works perfectly. All of this is going great. It's all the way to just a couple hundred meters above the surface of Mars. And it's supposed to, as you can see, it has these legs there, and it's supposed to deploy the legs before landing. So it's got these thrusters, it's firing, it's time to open the legs up, fires those pyros that we were talking about earlier to let the legs spring open, and it just then kills the engines and falls to the ground. And we lose it right there at just the last moment, basically, before touching down safely on the surface. And so when we went back and looked at the design, we realized what happened was there are sensors at the bottom of those little feet that you see on those legs. And those sensors are designed to be contact sensors. So when you touch the ground, you kind of hit a button and the button kills the engines. Well, the pyro created a shock in the system that made it look like the button had been hit. And sure enough, we killed the engines and just fell the rest of the way to the surface of Mars. And so from this, things that we do today in modern spacecraft is we don't let a single data point take out our system. So if you get one error that says like it looks like on the surface, you're like, no, you got to hold that error for 3 seconds before I believe the data. Or I need multiple sensors. I need 3 sensors at the same time, all telling me the same information. So we do a voting scheme, right? We let like multiple sensors vote on what is the right answer. And again, another lesson learned, kind of unfortunately the hard way, with our Mars missions, and we incorporated that into future missions. Now the good news is we've been super successful since this time. This is me working this is like 2007, working on the Mars Curiosity mission, and you can see what behind me is a huge set of racks. Those racks are all designed to simulate the environments that we see on the way from Earth to Mars, as well as on the surface of Mars. And if you look at the very left, you see like a box with a bunch of cables that are coming out of it. That's the engineering version of the computer that we're sending to Mars. So that table is actually the entirety of a Mars rover that's just spread out on a table. And we test and we test and we keep testing to try to figure out all the different ways that things can go wrong and fix them essentially in software, so the spacecraft has a way of taking care of itself. And it's tricky because Mars is anywhere from 4 minutes to 20 minutes away at the speed of light, which means that if you try to send a message to it, it takes at least 4 minutes from Earth to Mars. And so when your rover is trying to land on the surface of Mars, you can't joystick it. There's no, you can't like video game kind of like land it, because it will be a 4 minute delay at the least. It's actually 8 minute delay, because you have to see the picture that you're looking at and then react to it. So we would never be able to land the rovers on Mars if it wasn't for sort of the spacecraft autonomy, the smarts that we built into the spacecraft to take care of itself. And then we test that as much as we can. So what do we learn? Like, we learned a bunch of different things that I hope people can kind of take and apply, like whenever you're working on a project. And these are, I'll kind of go through these really quickly, but like we go through peer review, which is like, you know, maybe you have a great idea and you want to share it and you review it with a bunch of your friends or your coworkers and you say, here's my great idea. Like, can anybody give me feedback on whether it's a good idea or, you know, are there flaws in my design? In our case, we like to what we call expect the unknown. So again, we like say, what would happen if this thing went bad? Like, even though we don't think it's going to go bad, we sort of prepare for like a symptom. And like, if you're thinking like as a, you know, as a kind of a doctor or whatever, right? You might be like, well, I'm not exactly sure what went wrong with this person, but I can tell they have, you know, a cough or a sneeze, and therefore you kind of be like, at least I can give you something to treat that problem, even if I don't know exactly what's causing your cough or your sneeze. We do what we call verification and validation. This is where we test everything. We test what we designed. So we say, like, if this measurement is supposed to be 100 centimeters, we go and prove that it's 100 centimeters, and then we validate, which is saying, did we design the right thing? So, you know, for example, let's say you want to sample a bunch of places on Mars, and you've got to prove that you say, like, I'm going to make a rover to do the job, to drive around and, you know, gather samples. But then you also have to prove at the end of the day that the rover you designed was the kind of rover that can go and grab a bunch of samples. So not just did I design the rover that I said I was going to design, but does the rover do the job it's supposed to do the way I meant for it? And then again, plan for failure. We know things are going to go wrong. Not everything we can kind of prepare for in advance. So we try really hard to say, like, again, the what if scenarios. And last but not least, of course, is try to learn from other people's mistakes. You see somebody else making a mistake, there's no reason for you to have to repeat that mistake. You can learn from other people's mistakes. I do it all the time. That's the story of Mars. So let's talk about Curiosity's landing. This is August 5th, 2012. You'll see snippets of me in this clip, but it is the landing of the rover on Mars in the evening here in California. Is there audio to this?
If there's supposed to be audio, no, we're not hearing anything.
Okay, so the audio is not working, so I'll describe it. So we are at the top of the atmosphere. We're going 13,000 miles an hour. It's about 20,000 kilometers an hour. We are trying to decelerate by using the atmosphere of Mars. Mars has enough of an atmosphere that you can't ignore it, but not enough that it can slow you like on Earth with parachutes and alone. And so we actually see about a huge amount of acceleration. It would be about 12 times the force of gravity on right now as we're trying to slow down. So we get through the top of the atmosphere, we open a parachute. This is the largest parachute that we've ever built for faster than the speed of sound. And so it works successfully. And now we take off the heat shield that was protecting us at the top of the atmosphere, and we're looking for the ground with a radar system. So our radar is constantly pinging the ground. There's me. We're pinging the ground. We're trying to find out where the ground is, and we fire these thrusters to start slowing us down a little bit. Again, parachute's not going to get us all the way softly to the surface. It's still too fast. And now we know where we are relative to the ground, and we're going to do a trick that nobody has tried before on Mars called the sky crane. And this is where our jetpack stays above us and hovers and slowly lowers the whole system to the ground on cables. And we did this for a couple of reasons. One of these is it's technically a pretty great way to land. Yeah, and we were successful. There's a lot of excitement and emotion. That's right, like everybody's really jazzed. I cried a lot. It's no big deal. And we did this. So we did that sky crane thing for the first time because airbags wouldn't cut it. Our rover got too heavy and too massive. So, like, you know, airbags, right? You got to inflate some volume. The more mass that you need to slow down, the bigger the airbag has to be. So the airbag keeps getting bigger and bigger. It doesn't work great. And then we use the rocket engines on top because we noticed that when you put the rockets on the bottom, you actually sort of start carving out the ground below you, right? So, you know, think about it. The rockets are firing straight into the ground right below, right when you're above the surface. And if you're in a very dusty place, you're worried that you're just going to kick away a bunch of dust or, you know, basically create a hole in the ground. And then your rover is just going to be in a hole in the ground that it can't necessarily drive out of. So we said, what if we move the engines up top and we control the system? And the other thing that's kind of clever about this, which I know, like, SpaceX is amazing, they're landing the rockets, but if you've ever tried to balance something on your hand, like a baseball bat or whatever, you know how hard it is to balance something on the top of your hand. You have to, like, constantly move the bottom of your hand, and it's usually will fall off. But if you're dangling something like a yo-yo, it's pretty easy to move my hand and control exactly where the yo-yo is at the bottom of my hand. So it's also a simpler system in some levels than trying to land with the rocket engine on the bottom. So we were very happy that, of course, that worked out, and we're building another rover today here at JPL that is going to launch in July of 2020, so in a little less than a year, and arrive in February 2021. And it looks a lot like Curiosity. It's going to land using the same technique because now we've proven, hopefully to ourselves, that it works. There's still plenty of things that can go wrong, but we think we know what we're doing. And so when Curiosity landed on the surface of Mars, we got this amazing picture. This is the very first picture that we took, and it's it's about 3 p.m. on Mars, so kind of the the afternoon shadow there, and you can see the shadow of the rover being cast on the ground, and sort of just out of good fortune, the sun is straight behind us, and right in front of us is Mount Sharp, which is actually the destination for the rover. So the rover had to land in a nice flat place, which you can see in front of us is pretty flat. That's called Gale Crater. It's the floor of a crater that we know from the orbital pictures looks like it had water in it at one point. And we want to go to Mount Sharp because Mount Sharp is sort of like the Grand Canyon, and you can see layers. And wherever you see layers, you can see like different water levels had been at different times, different sediments were deposited, and maybe you can find out what Mars looked like, over time. So that's kind of the idea of why we went there. But it would only be a few months before we had our own anomalies, our own issues. And February 27th, 2013, here we are. We haven't quite gotten to the full mission because we're still checking out the rover, making sure everything works after landing, fixing some stuff. And we are 1 month away from the time that Mars disappears kind of behind the sun. And when Mars goes behind the sun for us, it is about 2 weeks where we cannot talk to the rover because we cannot send radio signals through the sun. And so we're sort of worried about our rover being safe for 2 weeks without talking to the ground. This clip won't work that great, but that morning we come into work and we see what's happening is the rover isn't responding to our commands. So we sit there trying to figure out exactly what happened. That's me. I'm working this anomaly now. And what we notice is that the rover has sort of stayed awake throughout the night, even though it's supposed to go to sleep every night in order to recharge the batteries. All right, so I don't have a clip video in there, but so what happens is we're looking at this data, we see that the rover's not going to sleep, and we're trying to diagnose it all within about 2 weeks before Mars goes behind the sun, or 3 weeks before Mars goes behind the sun, and we can't talk to it anymore. And so what we have to do is come up with a thing. And we thought in our design that we had protected ourselves against this because Curiosity comes with 2 computers, and the design is such that if one computer isn't working, the backup computer is actually supposed to take over for the first computer. We thought we had designed. So again, we thought we did our job right the first time. But it turns out the first computer was doing just enough to pretend like it was okay. So it was telling the backup computer, like, I'm fine, I'm fine, I'm fine. But meanwhile, everything outside of telling the backup computer that I'm fine was not really working the way we designed it to. And we were worried that what would happen is if the primary computer kept staying awake and didn't sleep during the night, the batteries would start to discharge. We go to basically, 1, we could damage our batteries, but 2, we would just reset as the power got low. And then when we reset, we would still come back to the computer that wasn't necessarily working. And so we were a little nervous about that. And so what we did is we designed a set of commands to try to force us to swap over to the other computer. We managed to do that all in the span of about 2 days. We got on the backup computer and we figured out, luckily, because our 2 computers can talk to each other, from the backup, which is now the primary computer, we would pull data from the broken computer across, and we were actually able to even write a new version of software. So imagine, updating your computer software here on Earth, but we have to do it now with, being 100 million miles apart, and sending that data back and forth, updating the version of software, and then having to leave the rover alone for 2 weeks and kind of hoping that it made it out the other side. Sure enough, we've made it out the other side. Curiosity has been operating successfully since then. This is a selfie that we took on Mars of the rover here. This is on Mount Sharp. This is taken just about 2 months ago. You can see the dust that slowly settled on the surface of the rover. And we've been able to determine, some pretty incredible science with the rover, specifically that where we landed was a very warm, wet environment in the past. And that the water that we found or would have been there about 3 to 4 billion years ago is the kind of water that we think you and I could have drank and could have even supported life as we know it here on Earth. So we're sort of finding evidence that Mars in the past was a place that life could have survived. And now with our next set of missions, the hope is to send, again, life detection, as well as bring samples back to Earth, maybe to help for finding life in those samples. Again, just some more recent pictures. Here's us drilling into Mars. So we carry a drill with us to help us kind of get the sample from within the rocks. We're able to find evidence or organic chemistry. One of the reasons why we couldn't find organic chemistry back in the 70s was because looking at the surface, it is there is perchlorates in the surface and they react. So they kind of damage those organic chemistry compounds. But if you can get into a rock, you can actually find the compounds are preserved. And one of my, some of my favorite pictures here. Here's a sunset on Mars. Sunsets on Mars are blue and not orange and red like on Earth because of the way the dust in the atmosphere works. So during the day, you sort of see reddish skies, orange kind of skies, but at night, as the sun is setting, because the light is traveling through all the dust, it sort of scatters the blue light towards you. And so you get kind of blue sunsets on Mars. And then my absolute favorite picture that we've taken is this beautiful picture that we took back in 2014, looking back at Earth, and there's the what you see in front of you is the craters of Gale, the walls of Gale crater in front of us, and just a single little speck. And if you super zoom in, you can actually kind of see a neighboring speck that's also slightly bright, which is our moon. But it's all about reminding us that this is why we're here, is to sort of help understand our own story in the world, and sort of our own context of what it means to be human and to exist on this planet together. And so there's something really special about having that perspective of being able to look back at our own world, and that's that little pixel is all of us. So it's kind of a very powerful experience and motivation to continue on this mission, and of course to hopefully get it right so we can keep taking missions like Curiosity and surviving.